All right, welcome back. We are COMP2142. That's Game Artificial Intelligence 1 in the winter 2026 semester at Georgian. And it's week 9, part 1 of our broadcast and recording today. It's been a day already, my friends. And lots of stuff coming. Snow is coming. Winter is coming, as they say. Which is weird. But today we're talking about data structures again. Notice that we've been talking about data structures, and this is our last lecture around data structures. I think with this one, it'll prepare you, at least at a very high level, to understand some of the data structures we require for game AI, right? As well as general AI, which is if you want to, learn anything about machine learning, or if you're interested in learning about deep learning, reinforcement learning, all those kinds of different kinds of things that are out there, neural networks. A lot of the data structures that I've been talking about over the last few weeks, are the data structures we use in some of those other disciplines, right? So here we are with data structures 4. We're talking about graphs today. We're also talking, doing an intro to pathfinding, where we're going to be discussing Dijkstra's algorithm, which is a very famous algorithm. It's been out for a while. We'll talk about who Dijkstra is. And our lab focus today is mapping neighbor tiles on the tile map, how to do that. And there's a bit of a challenge for you. I'd like you, if you've downloaded the PowerPoint slides, please try the challenge before looking at the solution. I think it's a good exercise to get you guys your mind warmed up about how it all works from a tile grid perspective. So take a look at that. So we'll talk about those things today. Let's get into it with data structures, graphs, and then we'll. I'm going to be using for this lesson. I'm going to be using a copy of week 8. I mean. So here's week 9. That's the one I'm using, and it's just a copy of last week's lesson so far. So I'm just going to put this up on. DevOps. So again, these little links, that I'm giving you, there is no in-class exercise necessarily, but they're there for you to support you to see a solution, perhaps as a start to assignment 3. And that kind of stuff. We'll talk about assignment 3 a little bit today as well, because I know that's on some people's minds in terms of what to do, how to start assignment 3, and all that stuff. And so we'll talk about that. Assignment 3 is interesting because it has nothing to do with assignment 1 and 2. So actually, assignment 3 is actually assignment 2A. That's what I call it, because there's actually 2 kind of assignments. So we'll talk about that today. And yeah. Okay. So I gotta look at that. Ah, there it is. All right, so that is I'm just pushing this up on the initial one on DevOps, so you can see where we are today. And it's not a very large project relative to what we're doing. It's large for Unity. If you have like an 800 megabyte project in Unity or a 1 gigabyte project, that's big. It's like lots of stuff. But for Unreal Engine, it's like, not so big. All right, so let's get into this. I'm just going to, while we're waiting, I'm going to launch our project so I can be ready when I talk about these data structures. So that way we're going to do some work here a little bit. So a couple of example project parts that we're going to use. So I'm kind of going to that. Last week we did this, and what we're able to do is load our map a little bit nicely. You can see that there is a bit of a grid. We talked about the tile map a little bit, and we also kind of developed both a queue and a stack. We've done that so far. And this week we're going to be talking about graphs and what those are. So again, when we think about a graph, I'm not talking about a graph like, graphing something out, like a motion graph or something like that necessarily. When we talk about a graph in math, I know it's maths, here we go. It really consists of a set of vertices and edges. So a bunch of nodes, if you will. And think about a map, let's say, that we have in a city or a town, and with other cities or towns all connected to it. And a map of this type is considered a graph in mathematics. Okay, so that's what we talk about it. Each town or city is a vertex or node. Sometimes we talk about that. And the road that connects the two towns or cities is an edge. Edges are specified as a pair, V1, V2, where V1 and V2 are vertices in the graph, or two nodes. That's what they are. So these are a connection between, node 1 and node 2, as an example. And a vertex can also have a weight, which is sometimes called a cost. Okay. So here's an example of a graph. You have a bunch of vertices or nodes. Now this is a special type of graph called a directed graph, because you have pathways, and if we look at this a little bigger, you have pathways from node A to node B, let's say, but there's only one path that goes there, and it's one way. So think about that in game dev, what that means. Imagine if you have a path, but there's no way of coming back. Like, it just drops off, and there's no way to get back up, kind of that path. And there's some again, I'm going back to our case study in Elden Ring, where let's say there's a bridge and it's broken, and then you jump down and then you can't get back up on that bridge. It's just, it's only one way. That's kind of an idea. Or you go through a door, and then once you go through the door, that door shuts behind you. You can't go back, kind of thing. There's no backtracking, in this way. So that is a directed graph where you have nodes that have, kind of these arrows. These arrows are connections or roads, paths, whatever you want to call them. And you can clearly see that there are two roads out from A, but there's no road back. So you can't get back to A. It's, once you're gone for good. E seems to be a transit point if you're looking at this, right? Where you have, you can go from A to B to E, or you can go to A to B to C to E, kind of thing. So there's a couple ways in, but there's many paths out. Maybe E is some kind of room that has multiple doors, or maybe multiple paths, verticality wise, where you have maybe an elevator that goes down. You might have a stairway, that goes downwards as well, a broken stairway, let's say, because again, there's only one way. Sometimes you can't go back, up different places. So you have kind of like a hub of things that you can do in E. Okay, so this is also called a digraph, another way of talking about a directed graph. If a graph is not ordered, so there's no direction, it's an unordered graph, or it's just a graph. So here you can think about each node, node 1, 2, 3 as an example, as they are two-way connections. So we have doors that you can backtrack in this case. Okay, the difference is there is no connection between 1 and 6. Right? You have to notice that you can get to 6, but you have to go through 2 and 3, let's say, to get to 6. Or just 2 to get to 6, because there's a node that goes directly from 2 to 6, but you can't go directly from 1 to 6. Okay, so there is no pathway, and I think this is the idea. So there is no like connection that goes like this. Okay, there is nothing like that. Okay, and so because there isn't that, you have to be able to traverse, these nodes. This is a possible path, right, where I go this way. I could also go this way, and I can also go this way, right? Or I can also go from here to here, back to here, and then down this way. Those are all possibilities. You can also backtrack a bunch of times, but that doesn't make any sense. Okay, so so that's the thing that I want you guys to think about when it comes to traversing a path. When it comes to traversing this path, that's what sorry, I must make sure that I have that. There we go. You got to think about the possibilities. All right, so lots of connections here. 2 is special. You can see 2 is special because it has 1, 2, 3, 4 connections, right? And 5 connections, and so is 5. 2 and 5 are very nice because they have multiple connections, ins and outs, as opposed to 2. 3 only has 3 connections. So does 1, 4, and 6. They have like 3 connections each, right, as an example, but 5 and 2, they have multiple connections. Okay, so that's one thing. So a path, again, is a sequence of vertices in a graph such that all vertices are connected by edges. That's the thing. And the length of a path is the number of edges from the first vertice or vertex in the path to the last vertex. We're talking about a path now, not just like if I was going to connect a path. A path almost is if I like to think about it as an array of vertices that connect, or edges that connect nodes. That's kind of what it is for me, right? A path can also consist of a vertex to itself. That's also possible, where it kind of loops a loop, if you will, and it has a length of 0 because you're not really leaving that room. You're kind of coming back into that same node. And it could be something like where you have a hallway that kind of goes behind the room and comes back into it, as an example. Okay. So that is the graph. So let's talk about types of graphs. So again, in an undirected graph, edges are bidirectional. So this is an undirected graph. We talked about this. One thing to notice is that there's a couple of nodes in this graph because this is another type of graph. It's just another example of it. Notice that there's no connections between 3 and 6 and 2 and 5 directly, and 5. There's only one way in and one way out. Sometimes 5 and 6, if it was a tree, these would be called leaf nodes, right? But because it's a graph, they're called sinks. Sink, right? So there's nothing, you can't leave. There's only one way in and out of this place, so kind of like a dead end, as an example. Okay, so that's a type of graph, bidirectional. So there's also, we talked about directed graphs, as an example, again, directed and undirected, right? And also weighted. So weighted has cost. Now let me talk about cost for example. So if it's a weighted graph, then there's a cost to traverse each of the pathways or the edges. So example, let's suppose I want to travel from 1 to 6, right? There's a couple of different ways to get there. I could go through 2, and then let's suppose 4 is missing a number. Let's say 4 is also 1, right? So 1, 2, 4, and 1, that's 3, a total cost of 3 to get there because you add up all the kind of like the links, if you will, or the connections to get from vertex 1 to vertex 6. Let's also call it node 1 to node 6, right? You could also go through 3. So that would be like from 1 to 3 is 1, from 3 to 4 is 2, and then from 4 to 6 is 1. So that would cost a total of 4 points, right? 4, it's weighted at 4. Now weights and values, if you will, it could be a couple things. It's not just the length, but it could also mean the difficulty in crossing that link. It could be like, as an example, a difficult terrain. Maybe you have to climb. Maybe it's slow, speed-wise, so you can only go so fast, as an example. And there could also be other things that limit you. For example, there might be only, it's not just difficult, but in terms of the number of people that can traverse, the bandwidth is very low. Like for example, there's only like, instead of having a 3-lane highway, it's only a 1-lane highway, as an example, which is like, or a 1-way street, as an example. Or it's a 2-way street, but it's only like literally 1 lane. And so you have to wait for the other person to leave before you can go in. I don't know if you guys ever seen those kinds of roads, like for example, a bridge that you have to cross, but there's only room for 1 car, right? But it's 2-way, go both ways, okay? So again, one thing is an undirected graph is considered connected if there is a path from every vertex to every other vertex. So that means that there's like some connection between every single path. And a directed graph, and this condition is called strongly connected if it's directed, right? So it has arrows, right? Undirected means you can go back and forth, right? If a graph has an edge between every set of vertices, then it's called a complete graph. Okay, so that's just naming conventions, so you understand what they mean. So a lot of times when we look at a graph, it looks like a tree. We've talked about, in order for us to get to this point, we've talked about how to create nodes from a coding perspective right, to kind of indicate what's the next node. So that would be like a linked list. So once we understand how to make a linked list or a tree, we understand how to make a graph. That's why we have to build up to a graph, right, in order for us to get there. And we have to understand about stacks and queues as well, because we have to understand how to create paths. So I have a graph, but I want to make a path from the graph, right? How do I do that? I have to kind of link up all those things, create an array or some kind of data structure to hold my path, right, which is a series of these edges and vertices. So again, so the vertex class is a place to store nodes. So think about this as a node class, you know, and again, we can think about the node class, you know, it also works the same way in a linked list or some kind of binary tree, right? The node class is what we're talking about for vertices. So let's talk about the vertex class for a second. And if we're going to make a vertex class, again, a vertex, the name vertex could be substituted for node. I want a node or a starting point, whatever you want to call it. A room would be, this could represent a room or a place inside of a room that we'll talk about later on. A location in a room, you know, vector. But it needs two data members, right? So a vertex class is going to need some kind of label that identifies the vertex itself. So this is like vertex A as an example. And also some kind of Boolean that marks that if it's been visited or not. Okay, because we want to keep track of, when we have a graph, if that node or vertex has been visited. If it's been visited, we mark it with a check mark or a Boolean, true, false, it's been visited, right? The only method we need, you know, for the class is a constructor that allows us to, you know, instantiate, you know, the object itself and set up the label and the was visited node. So if we look at what it looks like, here's an example of a vertex if we're going to map it out as in C++. Again, I like to look at C++ a little bit, especially with regards to, with respect to Unreal Engine. So we have this class for F vertex, and in the public section we have everything. One of them is the label, and the other one is a Boolean, was visited. Notice that the small b in front of it, Unreal Engine, remember, converts that small b. It kind of, you know, removes it. It ignores it when it comes back into blueprints. And then you're just going to see was visited as the name of that property or variable, right? F vertex, again, is the name of the class, right? So that is the constructor function. And in the constructor function, what we do is we take two parts. We take a string, we take the string label, and then by default, we set up, this is initialization notation, right? So this is kind of the way we want to initialize variables. So instead of saying something like, you know, label is equal to in label, we just do this, right? So this is kind of initialization notation. So the colon means this is an initialization list, and we're going to initialize our property called label, right, with the in label parameter coming in to the constructor function. And then was visited Boolean, we're just going to set it as a default of false. So again, that's why the constructor function has empty curly braces. We don't have to do it in here. We could just do it with initialization notation. Okay, that's how C++ can work. All right, so that is your vertex representation. And now that we have an idea of what the vertex looks like in C++, we can continue. So I want to start thinking about edge representation. How do I represent an edge, you know, as an example? So I have, you know, this idea, 0, 1, 2, 3, 4. These are the vertices, and I have edges between 0 and 2, and 1 and 2, and 2 and 3, and 2 and 4. Okay, so I want to be able to map this somehow. So what we can do is we can use something called an adjacency matrix. So here's an adjacency matrix where, again, where it says V0, so V0 to V0, is there a link? 0 means there's not, and 1 means there is a link, true. So 0 is false, 1 is true. So is there a link between vertex 2 and vertex 0? Yes, there is. So therefore, we mark that one as true, right? Is there a link between vertex 3 and vertex 0? No, there's no direct link between these two things. And so on, until we create an adjacency matrix that looks like this. the beautiful thing about an adjacency matrix is you can actually see if there are, kind of connections between the things. So for example, vertex 2, right, has a connection between vertex 0 to vertex 0. It also has a connection to vertex 1, right? It also has a connection to vertex 3 and vertex 4. So vertex 2 is the hub, call this a hub, where vertex 0, 1, 4, and 3 are sinks because they just go in and out one time, right? So example, you only have one connection for vertex 0, vertex 1, vertex 3, vertex 4. Look, 1, right? These are all ones. So that's, again, I look at a way of looking at this, and it's a good representation when you're looking at it about all the connections, and this is how you can map an edge if you really want to as well. So it's a two-dimensional array that has all the details about all the connections in it. Okay, this is one way of thinking about it, right? Another way of thinking about it is that what neighbors are connected to it. If we were looking at this in terms of does vertex 0 have any neighbors? It only has one neighbor, which is 2. That means that's when we say adjacent, it's like it's connected somehow. Maybe there's some other a hallway that goes there or whatever. So the nearest neighbor, if you will, is 2. There isn't a close neighbor to 0, right? There's no direct links from 0 to any other node. You have to go through 2 from if you're at 0 to go anywhere else. So 2 is the hub. So again, one thing that you can see is you can see it very clearly. It's very visual. If I was going to make a, kind of edges, if I was going to represent edges, so again, let's say we have a main program like this, and then we can add a vertex, 5 vertices add. I can build up the vertex array. Let's say, for example, I have vertices A, B, C, D, right? I can add in, I can use the add method of the T array to add in all the vertices that I want, A, B, C, D, right? And, the graph itself might also have the ability for me to add an edge. Add edge might be a method that's part of my graph. I might make a graph class as an example. And then the edge will have the start and the end. So you might have that kind of relationship. So an edge between 0 and 1, an edge between 1 and 0, because it's bilateral, right? Can kind of go both ways. We need to map both directions. And actually it makes sense in the adjacency matrix as well. If you look at the adjacency matrix, right, and if I go from 0 to 2, right, so vertex 0 can go to 2, vertex 2 can go to 0, right? So I've got to map both of those directions. Otherwise, it'll be just a directed graph, a mixed directed or undirected area where I have a one-way connection and from one vertex to the other, and I have a two-way connection from, this vertex to that one. It's possible, and the way that might work is, I can go back and forth across this link, but I can only go back. I can only go forward. It's kind of weird, but it's possible. So in other words, I can have a directed graph, a directed part of the graph too. This is also something where I have an arrow that goes like this. So I can leave 0, but I can't go back, right? But everywhere else, because they're undirected, we can go in both directions. That's also possible, right? I can also, when I go to 3, I can't come back at all. Once I go to 3, it's a sink. I got to stay there somehow. That's also a possibility, right? So you can mix and match. I don't recommend this. It's kind of weird, especially from a world traversal perspective. How do you justify that kind of thing, right? So it's just a matter of if it makes sense from a the way you're mapping your world. So now that we have this relationship mapping that we can do, we can think about a graph. So here's a graph, and the graph class will have all the pieces that you need to make this work. So we can have several private variables. So again, a static constant num vertices. So that's something that we can always track. So the vertices we can use, instead of using the hard-coded number 20 as an example, that's the number of vertices it would be, then we can kind of use a constant here instead, and then we change that one number, and then kind of all the places we use num vertices as an example, instead of using a constant value or a literal like 20, we could just replace this number here and then all these changes, right? Which is kind of cool. A good way to do it. I have two T arrays. One of them is F vertex, which is a number of vertices, and the other one is an array of arrays. And this is the adjacency matrix that we're going to be creating. The adjacency matrix, again, is a two-dimensional array. So it's an array of arrays, okay? And then we have the number of vertices. Number of numverts is a way of keeping track of all the vertices. So we initialize numverts as 0. That's in the constructor function, right? And then what we're doing is adjacency matrix set number. So when you set num, it sets it up to how big it is. That's what you're doing with set num. Okay, with adjacency, because adjacency matrix is just an array, and set num actually sets how large it is. It kind of sets a boundary for how big it can be, right? And then we have a for loop where we go from 0 to the num vertices. We loop through the initial for loop, and what we're doing is we also set the number of vertices as a boundary for the inner array. So it's an array of a two-dimensional array with the same size, the outside and the inside, okay, as an example. So again, if we think about what an adjacency matrix is, it's like we showed here, right? And it's kind of in a square, right? Because it's like, the number of vertices on the top equal the number of vertices on the bottom, of vertical and horizontal vertices, right? Because you're making a perfect matrix, so same size on both dimensions. And because you're doing that, then therefore when we're making our graph class, then you also must make the outer and inner for loops when we're initializing the grid. The adjacency matrix, as an example, I and j dimensions, which is the horizontal and vertical dimensions, must be the same. That's all I'm saying. And then what this is doing is it's initializing each of the points in the initial array, the adjacency matrix, as 0. So this is initialization in here. That's what's happening in our constructor function. Then when we add vertex, right, we add a vertex and it's just a label. So it just adds a number of vertices. And remember, the vertex array is literally just an array of vertices. That's all it is. So it's just like, and it's of type F vertex. So we created the F vertex class right here. So this is what it's going. It's going to give you a label and if it's visited or not. That's what it's giving you. Okay? So back to that graph class. So that's what add vertex does. And when we do that, if the number of verts is less than the number of vertices, right, we want this to be less. Otherwise, if we try and add too many vertices, and then it goes outside of our dimensions, then we'll ignore it. Every time we try and add a new one, it just won't allow us to do that. Okay? But otherwise, it'll increment the number of verts that we're keeping track of, the number of verts that's inside of our our graph. So our graph in this case can hold a maximum of 20, but we don't have to add 20. We can add 5. It's just, this is num vertices is the kind of the boundary of how many we can add. It could be a maximum of 20 by 20. That's the matrix, right? So if I want to add an edge, then I need two numbers. I need the starting and I need the ending of the edge. So this is kind of the start vertex and end vertex. That's what this is. So what we do is we say if my start is less than the number of verts and end is less than the number of verts, because it has to be within our boundary, right? Then the ones that we've added so far, then the adjacency matrix, we kind of set the start and end to 1 and the end to start to 1, because remember it has to go bilaterally, right? Or bidirectionally. It's got to go that way, right? So both are going to be kind of added in. And then we can show a vertex, and the vertex itself is going to be, basically it's going to show something like, the vertex itself with the label, so vertex A as an example, right? That's all it's going to show. So that's kind of what it's going to be. We also can print the adjacency matrix for debugging purposes. So we can say print graph, and so what we do is a double for loop, just like we initialize. We do a double for loop for kind of outputting the adjacency matrix ij, right, as we go through, right? So each one, where we say something like, here's the row, and here's the column, which is what we're going to show. And that's really the graph itself. This is the graph, which is the graph class. It allows us to create a graph, represent a graph in C++, and this is the way to do that. Questions around this? So I'm working a lot with you on graphs, and like I said, with these data structures, because I want you to think about how would you represent this from a coding perspective or even a blueprint, right? So again, challenge for you is, if I was going to take this, I would want to create this as a blueprint. How would I do it, right? How do I create this stuff, and how do I test it afterwards? As an example. So that's the challenge for you to think about. I recommend always, when I give you these little exercises, I know that you guys are time crunched. You have a lot going on, but there's nothing wrong with trying to practice Unreal Engine and just creating these little, converting from C++ into Blueprint. I want to search a graph. There's two types of searches. I can do a depth first search, or I can do a breadth first search. Let me explain how this works. A depth first search, let's suppose this is what a graph looks like. Now we've drawn this graph kind of weird, right? But I want you to see that A is the hub, right? So this is where we would start. Let's say we start at the hub, and we've just drawn it this way. But remember, you can draw this thing, instead of looking like a little spider, you can draw it so it looks like a star too, right? You can make these links kind of up here, and you can put this link up here, so you can draw it kind of like where A is in the middle, right? Which is kind of what this is. So the way that depth first search works is you go, kind of down the depth of all the links first, and then kind of go across. So what you do is you go from A to B. Again, you're going down one, and then from B to C, from C to D. So it's like 1, 2, 3, and then from D you go back to the next leg, if you will, that comes out of, or the next link that comes out of A. So you've explored all this path, this path right here. You've completely explored this. This is the search, right? And then you go and explore the next path, and then you go and explore the next path, and then you go and explore the next path, and you keep doing that. And that is a depth first search. So you go all the way down. This is kind of like I want to do all the side quests first. So instead of me doing, going to the end here, I want to go to M, and that's going to, I'm going to fight the boss when I go to M. Instead of going right down this way, I'm going to go do all of this first and then go and fight the boss, okay, as an example. And that's kind of like a completionist route, kind of thing. I want to do it this way. There's another way to navigate, which is, I'm going to skip this one. It talks about how to do a depth first search here, but I want to jump to a breadth first search. So that's a little different. So this is where I start off at the hub at A, and then I go to the first node that's closest to me, and then what I do is I go back to this path, and then I go to this node, and then I come back to this path, and I go to this node, and this node, and this node. So it's almost like a way of searching this way. So I go from kind of like the breadth of it. So it's almost like a spiral. I'm spiraling out wider and wider and wider as I go. And the reason why you'd want to do that is you want to make sure that you've handled all the stuff that's closer to where you started, and then you kind of, you're moving out to the farther points. Both a breadth first search and a depth first search have their utility, right? So in many ways, a depth first search can be faster, right? Because if you're looking for something, like if I go back a couple of steps here as an example, and let's say I'm looking for treasure, and it's in one of these pathways, okay? Let's suppose it's in pathway G, okay? That's where it is. It's a node G. That's where it is. So if I do a depth first search, it's not, I've searched 1, 2, 3, 4, 5, 6 nodes, right? And then once I've done that, I found my treasure, okay? But if I do a breadth first search, right, and if it's still in G, I got to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 nodes before I get to G, right? So a breadth-first search is more complete. A breadth-first search explores the world a lot more deeply than a depth-first search, right? Because it's just going to, for a depth-first search, I'm just looking for that one thing I'm looking for, you know, and then I may not need to explore the rest of the world, okay? Best case solution for a depth-first search, right, it's right here, you know, as an example. Best case solution for a breadth-first search is, again, it's right here, right? So it's like the first thing. Worst case solution for a breadth-first search is it's way over here, an M, and it's going to be 12 steps to get there. And the same thing goes with the depth-first search. It's the worst case scenario is right here, right? Like way over on the other side. But sometimes a depth-first search will find it, well, oftentimes, a depth-first search will find it faster than a breadth-first search. Okay? So I talk here about how to do it, and so if I go back to the original one, so how does it work for the first one, right? You pick a starting point, which be any vertex, right? And then visit that vertex and push it onto a stack. So we use a stack to do this, and then mark it as visited. So we do that. And then what happens is go to the next vertex, and that is unvisited, push it onto the stack, and mark it as visited. And this continues until you reach the last vertex, okay, the one that you're looking for. Check to see if the top of the top vertex has any unvisited adjacent vertices, and if it doesn't, then you pop it off the stack and check the next vertex, and so on. So first you build up the entire stack, and then what you do is you go through and visit them. So that's how you do it. Use a stack for this one. Whereas a breadth-first search, it uses a queue instead of a stack, right? So you queue up everything. So find an unvisited vertex that is adjacent to the current vertex, mark it as visited, and add it to the queue, right? And then if an unvisited adjacent vertex can't be found, remove a vertex from the queue as long as there is a vertex to remove, and make it the current vertex and start over. If the second step can't be performed because the queue is empty, the algorithm's finished. So you can see that breadth-first search is a little less involved than depth-first search. But breadth-first search is, like I said, it can be as maybe longer depending on how you explore the world. So that's kind of the algorithm. I've given you the algorithm for doing both those searches, so you understand how to search a graph. So now we're finally today, after many data structures, we're ready to start talking about pathfinding. So you can understand. We've talked about all the foundational things that you need to basically can discuss not just pathfinding, but also decision trees and matrices and making making decisions in general. Okay, so before we start pathfinding, we have to understand what this does. Really, what we want to know is we want to go from point A to point B, right? As an example, and it could be a very simple algorithm. Often, though, autonomous characters like an AI doesn't know beforehand where they want to go, right? So we can give them a route, and this is pathfinding. A route or a path, right, is an array of nodes, kind of thing, like a series of nodes that you want to traverse, right? Could be a series of connections, edges from node A to node B and so on. So when we think about where pathfinding is, it kind of goes in between movement and decision making. So decision making we're going to handle next semester. So that'll be in semester 5. If you're going to join me on Game AI 2 in the fall, that's when we're going to talk about decision making in more detail. But right now, we've just finished movement. We know how to move around using steering behaviors. But now we're going to talk about using steering behaviors, but going through the shortest path to get there, right? So we want to go from A to B, but now we're going to, we have some kind of scheme to get there, right? So once we figure out what the target location is, the pathfinding algorithm takes over and works out how to get there, right? So that's the way to do it. It's a way of moving, if you will. Now, I have to specify this. We used steering behaviors in the first half of semester, and we didn't have a path. We didn't need to track a path or anything like that, right? And we can kind of point towards a specific location, and it'll try and get there. we need to use things like obstacle avoidance and you know, collision avoidance to get there sometimes, because lots of stuff is moving all at the same time. When you use pathfinding, what it knows about where to go next, right? It also can tell if the next location is an obstacle. It can tell because you know what that you know, you can use an adjacency matrix. You can also kind of peek into the next node that's connected to this node and say, hey, is there a path? Is there any kind of connection between here and there? Okay, yes, there is. Is that blocked? Like, is it an impassable node? Is it like a wall? What is that in front of me? Is it another autonomous agent that's in there? Because there's another autonomous agent in there, I can't move into that node because there's something else in there, you know, as an example. So obstacle avoidance and collision avoidance, when you look at some kind of pathfinding, as long as you have nodes or vertices that you're traveling through all the time, you're following a strict path, as an example, you can easily avoid them without the use of whiskers and all that kind of stuff, because you know what's in there. There's like, you can look at that cell and kind of say, you know. By the way, you can combine both of these two things. You can combine steering behaviors and pathfinding, which is kind of what we're going to do. So that's pathfinding. So back to graphs for a second. So, you know, there are two primary algorithms we're going to be looking at in this course. One of them is Dijkstra's algorithm, and the other one is A-star. Those are the two pathfinding algorithms. And they both use, you know, directed, non-negative weighted graph data structures. All right, so that's what it is, right? They don't directly use the geometry of the level, but some kind of basic version that's represented by this data structure, right? What we're doing, we're, you know, using a division scheme where our graph is quite dense. Right, so if I go back to this, right, let's suppose you can represent this as a graph as well, right, where because we're in a grid formation, you can see that there's connections between, you can't see them, but there's connections between each of these nodes, let's say, right? So so from the start, I can go in any one of these 8 directions, and because I can move in any of these 8 directions, you know, then we can assume that if we can visualize a node everywhere. There's a node in every space, you know, as an example. And there's connections between every node to every other node, right? Like to each of its neighbors, let's say. Okay? That's very dense. It's a very dense graph. We don't have to make it that way, though, right? For example, when we use in nav mesh, we have a much less dense graph. What nav meshes do, right, if you think about it, and we'll study nav meshes a little bit more another time, but let's suppose we use the geometry of the level like this. We draw a line like this, right? And here's an example of you know, how a nav mesh works. Okay, so here's kind of something. We use the geometry of the level itself, and let's suppose it goes there like this. And in the middle of each of these triangles, you have a node, right? So here's a node. That's kind of how pathfinding works with the nav mesh. So example would be, if I'm starting here, the next node would be here, and then the next node would be here, and then the next node would be here. That's how I would traverse this area. And nav mesh is interesting because what again it does is it uses the geometry of the level and all the stuff that's in it to create you know, kind of a pathway forward for you know, for your autonomous agent, right? So that's what it does. So example would be like these little areas here, which looks like kind of like a, you know, a part of a room. Maybe there's a pillar here or something like that. If you can imagine that these aren't mines, they're just walls, right? We would use all the kind of parts of the room to create these nodes. So for example, this is a connection. I've just drawn it a little bit. I've zoomed out a little bit. Let me just do that one more time, just to visualize, you know, this thing. And I'm going to use a straight line as opposed to me drawing what I'm drawing here. Let's just use this. So we can do that. We can kind of connect, you know, kind of these things. So we can make a line like this, and this is how the nav mesh is generated typically. it kind of connects all the geometry. This is a corner, so it uses that as a node, right? And or part of this graph like this. And you can see that this is kind of what a nav mesh does if we're going to make a less dense graph than what we have right now. Okay, I don't know if you see this, but this is kind of how it works. Okay, and maybe we do something like that as well. You can see that sometimes you see a, you know, something that looks like this, you know, and there's the other one. And that's kind of how it works. It kind of looks like this in NavMesh. When you actually inspect it, it looks something like this. And it uses, like I said, the geometry of this level. So again, if you think about it, you know, we have, let's draw circles now. So we have these areas here, and these are the nodes approximately in the middle of each of these triangles. That's what it does. It takes kind of like the center of the triangle. That's what it does. Let's suppose it's there and there. And these are all the possible nodes, right, as an example. And of course it uses these as nodes too. So this is a node and this is a node, because these are starting areas, right? So if I want to traverse from my starting point to my goal, right, then a nav mesh, because it's less dense, right, it kind of creates a path for you like this, from here to here, from here to here, and from here to here. And that's it, right? So then this is how you would move. Now you can use steering behaviors to do this. You would turn, as an example, just like normal. You might have a turn rate, speed, all that stuff that we've been talking about in the first half, right? But you can use this kind of thing, you know, to traverse the graph. That's how a nav mesh works. However, we don't have that, and we've created a division scheme where every single one of these things, you know, I'm saying this again just so you're clear on what we've done here compared to other things. What we've done is we've created each one of these things is a node, and it has a weight that goes from that node to the goal node. All right, that's what it does. We've also made it so that if we inspect the tile, let's look at tile 0. And by the way, tile 0, just to give you a sense of where that is way up here in the top left corner, right? This is the top left corner of our graph, right? So way out here, this is the top left corner. That's tile 0, and way down over here, that's tile 1599 as an example, because it goes from, there's 1600 tiles. It's a 40 by 40 grid with 1600 tiles. That means there's 1600 vertices in our map, right? As opposed to our graph, as opposed to, well, what I showed you earlier, which was like 8. So now one thing to note is this, right? Once we create our vertices, we can create them so that they're invisible in the world, and we'll talk about that later on, right? You don't have to use a grid. You can use just points. You can actually create them inside of a room specifically for that particular room, right? So map them manually yourself, or use a nav mesh, right? And that's what it does. And now you know you have some way of traversing from one node to the other, okay? And to find the shortest path between those nodes is not that difficult. You can find the length of the node, so that's one thing. And the terrain type, if you're traveling over water or if it's rubble or whatever, and then you can use those numbers to kind of feed into the AI movement pattern or the algorithm, so it can decide which path it's going to take to get to your character to attack them, or whatever they're going to do the easiest, or maybe they're going to do resource management, collection, or whatever. Okay, so that's how this thing works. We have a very dense graph if you think about it, because we have 1600 nodes. So tile 0, right, one thing we know about each of the tiles is if I type in neighbors, each tile has a neighbor mapping. Right now they say none. None means null. There's nothing mapped. We have no connections right now. We haven't mapped that. Today we're going to spend some time mapping each of these connections, right? So each tile is going to know about all its adjacent tiles, all its neighbors, right? Once we have that, it's almost like I'm creating a little adjacency matrix for each tile, right? And then once we have the knowledge, if each tile knows each of its neighbors, if we know that, then we can peek at the cost to travel to that neighbor, and if it's a lower cost than any other neighbor relative to where it needs to go, which is I want to travel to, to the goal node as an example, then it'll choose that lowest cost in order for you to decide where to go next. That's really it in a nutshell. Okay. So going back to this, we know that this is what we want to call. And now we also, let's remember weighted graphs for a second, where we have some weight. Now I want to point out that the weights, again, it's not just the length, so it's not just distance, but it's also time a lot of times. It could also be other costs. As an example, there could be other costs that are built into that or baked into that number. A bunch of little things that make up that weight, whatever that is. Okay, so it's not just like time. It's distance, it's difficulty, it's danger, it's whatever else you want to assign to that. There might be many parameters that you put inside of there to mix up that number, right? So even though it might be a very short link, it could be a very dangerous link, and maybe you don't want your AI to go across that dangerous link. Like it could fall off, or it's difficult to do, whatever. Maybe it has to climb up or down, whatever it needs to do. Something that takes time, maybe too much time or whatever, or maybe it costs health. There's a poison link. You can go across it, but you're going to get poisoned. So that's an undesirable link. So we kind of we increase the weight. It's going to have more of a weight there because it's, you can get poisoned. Something's really bad, that can happen. Or maybe there's other effects, not just poison, but slowness, like, or other kind of health damage or whatever it's going to be that is associated with going across that link, right? As an example, like, for example, lava. So it's not poison, but it's lava. You take damage, right? Kind of thing, instantly. Okay, so this is kind of what we can look at. We can look at a series of weighted connections between nodes, right, as an example. And then when it comes to mapping a path, let's suppose I want to find the path from, like what we said before, from A to C. We know that you have to go through B to get to C, right? You can also go from A to D to B to C. That's also a possible path. That doesn't make any sense because that's going to weigh more. It's going to cost more than going from A to B to C. So example, A to B is 4, and then B to C is 5. You add those two together, so the total cost to move from A to C is 9, right? But if I want to go from A to D to B to C, then it's going to be 11 and 5, which is 16. That doesn't make any sense, right? And if I backtrack a couple times, that also doesn't make any sense. I don't want to backtrack ever, right? Okay. So here's an example of that sparse node idea that I have. Instead of using a division scheme like a grid, imagine if each of the rooms, in the center of each room, there's one node, right? And usually what we want to do is we want to create a line of sight between nodes. You can do this too, manually mapping from one room to the other, where you can create a kind of like a connection between those two things, right? So you can traverse kind of rooms inside of on the interior of some kind of level, by using nodes that you've kind of put in there like this. Okay, and you can see that there's from this node to this node is a cost of 4.4, whatever that means. 5.4 from this one, 4.3 from this one. So to go from here to here, the total cost would be adding all these things up. Okay, as an example. Okay. So let's do an exercise. I want to find the shortest path between A to H. Can anyone tell me what the shortest path is? I want to go from A to H. What's the shortest path? You guys there? Can you hear me? All right. So A to H. What's the shortest path then, Logan, since you answered? You can come on the mic and say it too. You don't have to, type it in.
That A, B, E, H?
Well, let's see. So if we go A to B, it's 5 points, and B to E is 4 points, so it's 9, and then
Oh, no, that's not it. No,
E to H is 8, so that's like 9 and 8 is 17 points, right?
So I think A, F, G, H?
A, F, G, 8. That's a possible path. So you've mapped this one. I'm just gonna map that out. So this is a possible path, right? This is what you've said. That's possible, but so is this one, right? So this one is worth 15 points, but this one
Oh, yeah,
is
sorry.
worth 14 points, right? That's A, B, C, H. That's definitely a way of getting there. You could also go internally here. Like, you know, for example, you could try something like A, B, D. That's 9. A, B, D, 9, 11, and 5 is 16 points. It's also a way of going there, but you can also go this way too. 9 and 8 is 17 points, like what you did earlier. So there's many paths, you know, as an example, but I think the shortest path is probably A, B, C, H, you know, as an example. Okay? So how would we find the shortest path if we're using an algorithm, right? So again, there's many different algorithms that we could use, but the two most common are A star and Dijkstra. We're going to talk about them. But let's suppose here's the algorithm that I want to map. I look at my adjacent nodes. So in other words, if I'm starting at A, I want to look at B and F. I want to explore those two nodes. Okay? So I start with B, let's just say. Okay? It doesn't have to be B. I can also start the other way. It doesn't matter. But let's suppose I start with B. Okay? So I start with B and I say, okay, well, B has a cost of 5, right? And then I map F. F also has a cost of 5, right? So I'm looking at both nodes, B and F. What makes me go to B over F? They both have a cost of 5. I can go in either direction. Remember, one thing that you should note is that pathfinding it is blind. Okay, we don't know, we can't see more than one node ahead of ourselves. So let's start with B then, because both neighbors are the same cost. So I'm going to start with B. Okay, so we're starting with B. Okay, and then from B, now I want to look at all the neighbor nodes and find the lowest cost. So there is D, E, and C as an example. So I want to find the lowest cost. Well, guess what? D is low and E is low, but C is not. I wouldn't explore C right away. Okay, so so if I use that algorithm, so D and E, I might as well choose D first. So this is the second node that I'm going to go to. All right, so I'm going to go to the right node every single time. Okay, so now it's like A, B, D. Okay, from D, where can I go? I can go from D to E, from D to G, or from D to F. Right? Well, guess what? D to G is the lowest cost, so I go here because there's no things here. So this is the second node I try, right? Or the next one. Okay, and then G, all the nodes are the exact same, right? So going from G to E, that's the same. G to H, well, guess what? G to H, H is our goal node, right? So I'm going to do this one. As soon as I check out H, and H happens to be our goal node, that's the direction. So my first path that I'm going to try in this algorithm that I'm describing for you is, you know, which is not the shortest path. It's just the fastest path that I found, right? I found a path is this to this to this to this. Why? Because it describes a path to get there. So now I add it up, and I have 5 and 4 is 9, and 2 is 11, and 5 is 16. So that's my first number that I've kind of accumulated. Okay, but I'm not done yet with pathfinding, right? Because I'm going to put 16 down as a possible path length, and we're going to describe this as A to B to D to G to H, which is you know, kind of a path length of 16. That's one possibility that we're using. Okay, that's great. Now we go back, we backtrack all the way back to B. We've tried this left path of B, but now we're going to try this right path on B, right? We're still exploring B, okay? And so now let's get back to that. And we go here. So I'm going to use a different color just so we can see the second path we're mapping, okay? And this little algorithm, we map this one. So this is the second path. So we go from A to B, we're still at B, we go to E next. Okay, so instead of going to D, because B, D, and E had the same cost, 4, right? So we went this way this time, okay? And now what we want to do is from E, we have 1, 2, 3, 4, 5 possibilities, right? So, okay, so we notice that C is the lowest cost, so this is the next one we're going to go to, okay? And then from C, we're going to go to, we see that there's a way back to B. That doesn't make any sense because that's going back to where we started, right? And there's a path to H. So this is the next path we're going to go to. And so now we have a new path that we're going to map, right? I'm just getting you to understand how this little algorithm we're defining works. So it's going to go from A to B, from B to E, from E to C, and from C to H. Okay, this is the possibilities that we're mapping right now. Okay? So we found another one. And this time it is A to B to E to C to H, right? And the total cost there is A to B is 5, B to E is 4, and 3, right? 4 and 3. So 9 and 3 is 12, and 4, 16. So same cost. Right? 5 and 4 is 9, and 3 is 12, and 4 is 16. So that's the same cost as well. So there's two viable paths, and they have the same path length. Okay? And they have the same number of nodes and the same number of hops that we've taken as well. That's what we've done. And then we're going to use, I know this is exhaustive, but it's a good exercise for you guys to think about how this can work potentially. I'm just going to use another color here. Let's use the green color, right? So we've explored, for B, we've explored for these two paths, and now I'm going to explore C, okay? Because I've just chosen to start with B, right? So I go from A to B to C. This is the one I want to explore next, right? And from C, I could go back to E, right? A, B, C, E. I could do that, or I could go down to H. Well, C to E has a lower cost, but H is my goal node, right? So because I know that, I choose H. See, what I'm always checking to see is that one of our nodes that are adjacent, is that the goal node? Then I can shortcut. I don't have to do the other one because I found the goal node, right? So that is my path next. So again, if I was to draw this, and this is just, I'm not going to go through every little possibility, but because I would have to backtrack and all that stuff, I'm not doing that. But you get the, I think you get the idea here, right? Where I do one of these. So now you can see that A to B is 5, B to C is 5, and that's 10, and C to H is 4, which is 14 total. That's a shorter path than the other two. And so therefore, what I found is a shorter path that goes from A to B to, to C to H directly, right, without going through E. And that is a total cost of 14. And eventually we'll find out, once we do an exhaustive search of everything, that A, B, C, H is the shortest path. But only after an exhaustive search, which means I keep going, mapping, until I find all the possible paths. And once I find all the possible paths, then I can decide which path I'm going to map is the shortest path. This is Dijkstra's algorithm, okay, for the most part. One thing that we know about Dijkstra's algorithm is it explores the game world in a very detailed manner, right? It's a lot slower, way slower than using A star, which we'll talk about later, okay? But this, in its way of doing things, is Dijkstra's algorithm for the most part. So let's talk about Dijkstra. Who is he? See, he's one of the most famous, programmers. In many ways, a lot of people think of him as one of the fathers of AI. His algorithms are used not just for game AI, but also for other things as well. Specifically for things like, deep learning and other things like that, because finding the shortest path is not just what we use them for. We use Dijkstra's algorithm for searching, right, and exploring, right? Different nodes, kind of in a directed graph or undirected graph. So Dijkstra's algorithm kind of works like this, where you can see that it's exploring all the nodes in kind of like this, breadth first search kind of idea. And if you notice what I was doing, I was using a depth first search when I was going through everything. That's not what Dijkstra does exactly. I was kind of showing you a little bit of Dijkstra. But realistically, what it should have done is I should have explored B and then F, and then from B I go back to B. So I know that B and F have the same cost. I go back to B, and then I start looking at C, E, and D, and I start mapping, creating an adjacency matrix for B, and I make an adjacency matrix for F and D, and I start creating matrices for all these things. So I explore kind of in a breadth first search, as opposed to in a depth first search, which is what I was doing, right? Okay, so that's what it kind of works like. So it kind of works like this. Notice how it's very detailed in terms of how it's exploring the game world. Imagine each of these nodes are in our example, because we have a division scheme that looks very similar to this, by the way. Very detailed, a very dense division scheme. This is an example of that dense division scheme. It kind of finds this obstacle, right? This division scheme, or a set of obstacles, let's say, because each of these nodes represents obstacles, like walls, right? And then what it does is it continues to search in this breadth first manner until it finds the goal node, which is right there. And once it does, then it backtracks through the shortest path until it finds, its way back to the starting point. That's what it does. Backtracking, there's many ways of doing this, but one way is to use a recursive program, a recursive algorithm to go back. As we add stuff to the stack, we pop stuff off the stack, and we create that. We create our our path, if you will. So that's how it kind of works. From a detail perspective, it does find the shortest path from any specified vertex to any other vertex, and it also explores the world as well. That's what it does. And it does this by using this thing called a greedy algorithm, right? A greedy algorithm breaks a problem into smaller pieces or stages, right? And determining the best solution at each of the stages. And then with each sub-solution, and when I think about solution at each stage and a sub-solution, I'm thinking recursive algorithm, right? Because I'm just repeating myself over and over again, and I can use a recursive algorithm or a loop to do it over and over again. So Dijkstra's algorithm, it creates a table to store known distances, right, from the starting vertex to the other vertices in the graph, and each adjacent vertex from the original vertex is visited, and the table is updated with that information about the weight of the adjacent edge, right? If a distance between the two vertices is known, but a shorter distance is discovered by visiting a new vertex, that information is changed in this table. So it basically updates this table as it goes, right? And the table is also updated by indicating which vertex leads to the shortest path. That's what it does. Okay, so kind of figures it out as it goes, kind of thing. So it spreads out from the starting node, like we talked about before. And the idea is, I'm just going to shorten it for you, so I'm not going to repeat myself. Cost so far. How much does it cost so far to travel from here to here to here to here? And then once you figure out, you find a possible solution, as an example, because again, notice that in that previous little diagram here, there are many paths to get to this goal node. Many paths. It's not just one path. You can go different directions. It's finding the shortest path that we want, which means keeping track of the total cost so far, right? As you traverse from one node to the other, as we explore the world, we keep track of the cost so far from a travel perspective. Okay. So that's what it does. And so again, if we want to travel from one node to the other, it stores this information. One way to do this, it keeps track of nodes in two lists, an open list and a closed list. The open list holds all the nodes that have been seen, and the closed list holds nodes that have been processed, right? So process nodes are the ones that we want to, kind of like we've seen them, we've gone through it, but we haven't. We've gone through and explored them all, like all the details. They're processed. They're done. Seen nodes are the ones that were okay. I've seen A, B. So example, from A, we can in the open list you might have B, C, and D. That might be part of A, kind of thing, because A can go from A to B, from A to C, and A to D. Notice it's a directed graph here, right? So that's in the open list, right? Because we've seen all these nodes. Now we're going to go to B. B is visited, right? Once we visit this node, it becomes part of the closed list. I've already visited it. Okay, cool. And so now what I do is, okay, I go from B to E and F are part of the open list, as an example, because we haven't visited them yet, right? And of course, you have a destination in mind. So the path, the way we generate the path, as an example, so let's suppose the goal node is G and the start node is A, right, as an example. We want to make this path between A to B to F to G. So notice that the open list is C and D, right? That's still part of the open list. We've seen these nodes, right? But we haven't visited the nodes, right? But we have gone to B because B was a place to, that we went to. So that's a closed node. A is closed too because we've started there. So A to B was part of our closed list. And we've also gone to E. We've explored E, but we realized when we went there that it's a sink. It doesn't go anywhere. It doesn't have any connection. So that's part of our closed list. We've gone and processed that node, right? And then we've also gone to F and G, and we realize that there's a path that we've connected. We have a connection between A and G. And then now we backtrack. So the path is GFBA, and that's how we map it. GFBA. Okay? So that's how Dijkstra does its node processing. Before we get to a priority queue, are you clear on some of this? Anyone is confused, or are you? I'm going through this in detail because once you have this in your mind, right, for how this stuff works, then you kind of understand like how pathfinding works. Once I've told you this stuff, I mean, it's just a matter of, these new things that you've never explored the thought about this or whatever, right? But once you have this in your head that this is a way of doing it, then you can make your own algorithm. You don't need a Dijkstra or whatever. You can start thinking about how I would do it if it was me, if I was going to find the shortest path without Dijkstra, right? And I knew the costs, adding up the costs is definitely a way, right? But I want to explore every node and I want to find the shortest path, the absolute shortest path. Then you'd follow Dijkstra's algorithm. It's going to find the shortest path, but it's going to take time and it's going to explore a lot of the world before it gets there, right? So it's not the fastest algorithm, and that's why we don't use it. We use Dijkstra if it's absolutely necessary to map every single node, as an example. And we also use Dijkstra if we're using a division scheme that's a hex grid. If I'm using a division scheme that's a hex grid, Dijkstra by far works better than A star. Okay. Okay. So let's continue with the need for a priority queue. So why do we need this thing? Now we're talking about going back to queues, which is a data structure. So again, remember a queue is just a lineup, and a priority queue we talked about last time is a way of kind of organizing our elements when we're dequeuing them in the shortest and the kind of ascending order, right? So when we dequeue an object from a queue, we do this in ascending order, right, and priority order, as an example, as opposed to the order that people arrived. Okay, so this is a new type of structure. It's a queue, but imagine if you're lining up at the, we're all lining up here, or we have our 15 of us, we all line up for Tim Hortons, as an example, but for whatever reason, Liam, you've got priority, as an example. You're a VIP. So instead of you, even though we lined up all together, Liam, you get to jump the line and get your coffee first. That's a priority queue. It's based on, who is the most important or the lowest cost, as an example. So why am I telling you this? We have 8 neighbor nodes, right? We're going to do this today. I have 8 neighbor nodes for each of these squares, right? So again, if we're going to look at our idea of a division scheme that we're using, right? There we go. So let's suppose I'm starting here in this node right here. Then I have these 8 neighbor nodes, right? So I have this one, all these nodes, right? These are all the 8 neighbor nodes, okay? And let's suppose I'm here, and what I want to do is I want to go to here, And let's make that a different color. Let's make it red. I want to go to here. Okay, this is my destination. You know, as an example. And when it comes to defining, you know, kind of our path, let's suppose that because we're using, I'll change the color again, back to green. Let's suppose that when we put a color or number for each of these things, that we each of these, you know, kind of neighbor nodes has a value to go to the next node, right? So, and it's just not a random value. I want you to think about it as a pre-cached value, or you know, a way of it knowing itself. Which one of these nodes is closer to this one? So if we were to measure, it's almost like saying, well, if I count from here to there, and I can go across diagonals, you know, to get to there, then I can go this way. I can, from this node, it's 1, 2, 3, 4, 5. So this node has a cost of 5 to it. Let's suppose. Okay, and this node 1, 2, you know, 1, 2, 3, 4. So this node has 4 costs, right? Like where I am right now. Okay, and this node is 1, 2, 3. This is 3 costs. Okay, and this one is 1, 2. Okay, we're going to kind of do this again another day, but I want to show you this for now. And this one has a cost of 1. This cost that I'm putting on here is the cost so far. Cost so far. I've already added up. Imagine if every one of these nodes in our very dense graph has a cost of 1, right? They're equal cost, you know, as an example. Let's suppose. So then what about this one? So from here, this node, it's 1, 2, 3. This is also 3. Okay. What about this one? 1, 2, 3. This is also 3. And what about this one? So 1, 2, 3, 4. This is also 4, right? How about this one? This is 1, 2, 3, 4. This is also 4. Okay, you can see how I'm planning this out. This one is 1, 2, 3, 4, or 1, 2, 3. Actually, I can go diagonals, 3. This is probably 3. This is 4 probably, right? Because it's 1, 2, 3, 4, right? But this is 3 because it can go this way. It's right here, right? And this one is 1, 2. This one's 2. And this one is 1. You know, and this one's 1. And this one's 1. All these ones are 1. Okay. I'm just, you know, showing you because this is our goal node and this is 0 because this doesn't count because we're at the goal node right here. Okay. And this one is 1, 2. Just going to fill them in. This one is 2 for now. And that one's 2. And this one is 2. And so is this one. And you get what I'm doing here, right? Kind of creates in a weird circle, right? It kind of creates this area where all these ones out here, so 1, 2, 3, so this is 1, 2, 3, this is 3, and so on. And you can see that as I map these nodes, right, with each of the costs, it makes it easier for us to understand where to go next, right? So what about this one then? What's this cost? So this is 4 as well, right? Here's 4. What about this one way over here? That's 5, right? And this one, well, that's 5. And this one down here, that's 5, right? So if we look at our nodes and I want to find the shortest distance between, you know, my start node and my goal node, then I have these numbers here that I'm going to load into a queue, right? And let's suppose I use a clockwise direction to load them onto the queue. I have to have some method, like which one do I choose first, right? So I kind of load them starting at the top. So I go top, top right, right, bottom, bottom left, left, top left. That's the method I use to load all the things into the queue, right? So if I did that, then I know that I'm going into a lot of detail here, guys, but I want you to get it, right? And most of you have, I'm sure. But then that means that when I load my queue, it's 4, 3, 4, 4, 5, right? 5, 5, 5. That's what my queue looks like when I load this up, right? Where if I can put commas in there to show you what these are, this is what it would look like from each element in the array or in the queue, right? So, but now when we dequeue, I want to look for all these elements and I want to look at the lowest number. So what my queue reorganizes itself, right? And it looks like this. It sorts them. Like this. And now 3 becomes the lowest, the priority. This becomes the priority because my queue sorts itself. It's like a sorted queue. That's why it's called a priority queue. And so my next position in the queue becomes this. And then this. And then this. And finally the goal node. That's what we're doing, okay? So we're doing something different. Now how we get those numbers, 4, 3, 2, 1, 0, that could be Dijkstra's algorithm, that could be A star, that could be any algorithm you want. Prim's algorithm, there's a lot of different algorithms that do the same thing, okay? But we're only going to explore 2 of them in this semester. Okay, so that's kind of the way we want to do it. Questions around this? So the detail here is how do we assign values to each of our nodes, our neighbor nodes? How do we do that? Well, first we need to map them. So each node has to know each of its neighbor nodes. It has to have a reference to each of its neighbor nodes because we're creating this dense graph, right? You know, as an example, our graph has 8 neighbor nodes, but you can have a graph that only has 4 neighbor nodes. And that means that you only care about, you know, top, right, bottom, and left, but the diagonals aren't mapped. You could say that. You could say that each of the diagonals here, these diagonals here, are not mapped at all. There's no, you can't get to them. You can't go diagonal. You can only move in this pattern. If that was true, right, then we couldn't go this way, right? Even though the distance is, it says 3, that's not how it would be actually, because we can only move up, you know, like in that squarish way. Then so this wouldn't be 4, right? This would be 1, 2, 3, 4, 5, 6. So our numbers would change. This number here would be 6, and so on. And this number here would be 5, and so on, right? So it would kind of be going. And so each of these numbers wouldn't have, the corners would also have a value, but it'd be, this one would be 2, this one will be 2, this one will be 2. So the corners would all be one number higher, typically, because you'd have to go this way, right? In that way of doing things. So we're allowing, in our algorithm, I'm going to allow 8 directional movement, and so that way you're going to see this kind of pattern. But if I only allow 4 directional movement, like up, down, left, and right, then you wouldn't be able to see this pattern at all. Okay, so hopefully I know I've exhausted this thing with you, but I wanted you to understand the basics of what we do, you know, how we move things around. So that's why a priority queue is important. It allows us to traverse, you know, a weighted path by popping in the highest priority or the lowest number in our queue. Now, what about if there's 2 numbers that are the exact same? It's going to pick the first one. And so when it comes down to this, right, I want to specify this. If we're using Dijkstra and it picks the first one, it's going to come back and it's going to pick the second one that has that small one. That's the smallest number. So example, if I had 2 3s and the rest 4s and 5s, you know, in my queue, then I pick the first 3 and I explore that path, and then I pick the second 3 and explore that path, and eventually go to the 4s, right? Because there could be a shorter path. You don't know. Remember, pathfinding is blind. We don't know what the next one and the next one and the next one's going to be, right? However, when we have a smart tile, which is what we're creating in our example, each tile knows what the other tile, we can look at all the neighbors and have a value that's stored inside of that tile for the next tile. right? So we can quickly get to the shortest path because there's going to be a couple of shortest paths probably per tile, right? And we're going to try and explore both of them, okay? So here's what a priority node would look like if we were going to program it. The priority node would have a node index, right? So the node index would be, whatever the number is in the path in the graph, and then some kind of cost. And I'm calling it a G cost, right? Which is the cost so far. That's what we're talking about here. And so then what we'd have is one thing that you can do with C++ and C#, those two languages specifically, is you can do something called operator overloading. Does anyone know what operator overloading is? So we know we can overload. Thank you for that. We know we can overload. Actually, let's go back. Let's ask that same question I've asked before. What's the difference between overloading and overriding? Remember those two words again? And someone answered this before. So what's the difference between overloading a function and overriding a function? Do you guys remember? So no one's really answering it, but there we go, Chris. Thank you, Chris. Overloading is when you can have multiple functions with the same name but different parameters. Excellent, thank you. That's overloading. Overriding is when you have the same name, right, same parameter, different, definition. And usually overriding happens in a child class. So you have a parent class, and then you have a child class, and the child class inherits the function from the parent class, but then we redo the details of that function. We override that function, so it's going to be something different for the child compared to the parent. It's a specialized version of the function. That's overriding. Overloading allows us to have many different parameters that use the same function name. So what about overloading operators? Well, we have a bunch of standard operators. The plus operator, which is the addition operator, the minus operator, and we also have comparison operators, the greater than sign and the less than sign. In C++ and in C#, those two languages specifically, we can overload those operators as well, where we have different things that we can put on either side of the sign. So for example, if I want to compare nodes, and I want to compare what's less than, right? How do I determine what's less than, which node is less than the other node? We're looking at the node itself, an object, not a number, right? An object needs to have some kind of value associated with it. In this case, our case, the value of an object is its cost, right? So we need to overload the less than operator here as an example, and this is how you would do it. This is operator overloading in C++, and then we would compare the costs of one object with the other object. So what this means is the operator on the object on the left is compared with the object on the right, okay? And then we take both the G costs from each of the same objects, the same object we're comparing. We're comparing apples and apples as an example. And then what we're saying is if this G cost is less than this one, then this one is less than. It's going to be true, right? As an example, or otherwise it's going to be false. Okay, because it's going to return a Boolean. That's what the comparison operators do. So this is really cool because what we can do is we can create a custom comparator. That's what it is, a comparator, if you will. I feel like saying sensor, comparator, right? I'm comparing two things, and I'm saying, well, which one am I going to choose? Which node? I'm going to choose the left node or the right node. Well, it depends on the cost, right, that each node has. That's what I'm doing. All right, so that's this stuff. So then once we have that overloaded, operator, then the rest is interesting. We can on-queue and de-queue. That's because it's our priority queue, as an example that we're going to eventually write. I'm going to write this with you in C++. And what we want to be able to do with this class, as an example, is we want to on-queue. When we on-queue, we add a priority node. And the priority node has both an index and a cost. That's what the priority node has. And then what we do is we sort. That's a way of doing it. This is a really quick way of doing it. When every single time we add a node to the queue, we pre-sort it. That's what we're doing it. And that's kind of a trick that we're using here, okay? So why is this great? Because instead of us doing any comparison at all, we're just going to take, you know, the lowest cost as it is. And we're going to sort it. When we do a sort, this is the thing that we want to do. That sort is going to be based on we need to overload. Like I said, we have to do this first. So each of the priority nodes has to have an overloaded comparator operator so that the sorting works, right? So this is per node. Each node looks like this. But then when we do the sort uses the comparator operator, the less than sign, to determine which one is going to go where, okay? And once this is done, then when we dequeue as normal, because we always remove at the 0th element, right? The element in the beginning, right? And the rest is the same. So this is our priority queue, and our priority queue works amazing when it comes to sorting which neighbor we're going to choose next. That's what it does. And when I dequeue that, I can put that neighbor onto the path, a potential path list, if you will, that I want to create. Okay, so that is my priority queue class. And then what we can do with Dijkstra, here's Dijkstra's algorithm, and I put this into C++ for you as well. So we have the start vertex and the goal vertex. And if the start vertex is greater than or equal to the number of verts, or the goal vertex is greater than or equal to the number of verts, return, which means, well, we haven't found anything. We've searched everywhere, and I'm returning nothing. I'm not getting any path from this. Otherwise, if it's not this, then I have an array of distances, an array of visited nodes, if that array is visited, and an array of previous nodes. And each of these things are parallel arrays. That's what they're like. So I have 3 arrays, distances, visited, and previous, and they're going to use the same vertex, the same index in here. I have a priority queue called an open list, right? That's the open list. And I have a T array, which is the closed list. This is the process nodes that we talked about before. And then what I do is distances, which is an array, I kind of set up distances, the visited array, and the previous array with the total number of verts that I want to use. Num verts might be 20, or whatever the number maximum hops is going to be, as an example. And once I have this maximum hops, like I want to do like only, I don't know, my path length maximum is 40. I'm not going to go longer than 40 hops. That's like 40 different nodes that I'm going to go to. Whatever that is, it will stop, when it gets to that point. Okay. And then I'm not going to go through every part of this thing, but pretty much what it does is here, instead of using a recursive function, I'm using a while loop. A while loop, even if you talk to Connor, a while loop can a lot of times replace a recursive function. So instead of me calling the function itself, we can just use a while loop to this, and it'll process each of the neighbor nodes in this way. Okay. So challenge for you is do a couple things. One is, what if we took this priority queue and we took this priority node and made them into blueprints? And then could you use Dijkstra's algorithm? Could you recreate Dijkstra's algorithm to create to find the shortest path, using the stuff that we have? And that's where I want to pause, right? So let's take a short break. We've gone about an hour and a half, and I've shown you kind of the algorithm. So we talked about Dijkstra's algorithm, which is kind of a greedy algorithm, but it's a breadth kind of search. It kind of spans out and explores the game world. That's what it does. And after it explores the game world, then it knows it's explored many of the nodes and finds the shortest path and puts that inside of a, kind of an array. What we're going to probably have, and this is what you would do if you were actually going to do this properly, is Dijkstra's algorithm would have a path array, right? Where each path is an array of arrays, right? And so kind of a two-dimensional array in some ways, right? Where the second array, or jagged array, we can call it that way as well, right? Where the second array itself is a path, right? So A, B, D, C, or whatever that is, right? And then each of the paths, each of these things is going to have a total path length. So it's going to have two parts. The path is going to be, it'll be a special data structure. A path will be a data structure which has the nodes in the path and the total cost, right? And what we do is that path, as an example, is going to be an array of paths that we have that it's going to keep track of. As it continues to find, pathways to the goal node from the start node, it's going to map all of them. And then after the array is done, as an example, it can look for the shortest one. Which one? There might be two that are the same length. So it could choose the first shortest path because they're the same length, whether it goes this way or this way. Sometimes it goes to the same place and it has the same path length. So it's just the way that you design your algorithm, right? Yeah, and so that's where I want to stop. Let's do a short break. Let's take 5 minutes, get a coffee or whatever, and when we come back, I want to get right into our lab, which is I want to map neighbor tiles, but I also want to do some practice with creating some of these data structures and blueprints. Okay, again, I'm doing this over and over again with you guys to make you feel hopefully more comfortable with some of this stuff, because it can be daunting. It can be, when you first look at trying to translate C++ into blueprints, your mind has to kind of flip a little bit and you have to think about how to do it. Vice versa too. I want to take a blueprint, convert it into C++. How do I do that? But we're going to get there. I want to try and continue to map this stuff out with you guys to make you as comfortable as possible with these topics, these concepts, and so that when we get into something more complex, like for example designing a decision tree, which is what we're going to do next semester, right? Next time we get together with in AI, we've already seen this stuff. We've seen some of these things. We've it's kind of gone into our mind. We've absorbed some of it, perhaps, so it makes it easier for you to understand. Otherwise, if we just go right into something like a decision tree, or a behavior tree right from here, yeah, you might know how to use it, but you won't really understand the underlying process at all, right? And so that overall, you'll have gaps in your knowledge, which is not what we want. Okay, let's take a short break, and we'll come back in about 5 minutes.